Hello Unity developers, today I want to bring your attention to a completely free tool that can help you with programming your next game in Unity. I am talking about an open source project called Signals. You have probably encountered this issue. Your character reached a level exit and you would like the game to respond to that. But for that you must go and find which particle to spawn where, which UI panel to enable, play an animation on the player, play a sound, load a new scene. Just finding all the different game objects and classes is a lot of work. This package solves the problem by allowing you to create global events. Signals calls itself a messaging package, but you also may find it falling under the category of a global event bus. The package will help you avoid nasty singletons, calls to find object of type, and other bad habits, untangling your code with what is known as loose coupling. Game or level managers are usually typical examples of tight coupling. Tight coupling is defined as a single class knowing a lot of information about other classes. The level manager knowing about the timer class, the player class, which audio to play when the level ends, different checkpoints, different UI panels. We want to avoid this as it makes extending your code harder and it is prone to having bugs. Enter Signals. Let's take a look at our first example. We have a single button and a big enemy tank we can damage with that button. When the health reaches 0, the tank is destroyed. Not much to see here. In the code, we can see the enemy script simply has fields containing its health and a reference to the slider. We also have a score field and a public getter for it, but that is for later. In the take damage method, we subtract our HP and update the UI. If the health reaches 0, we send a signal. To do that, we need to get our signal with a static get method on the signals class. This method requires you to provide the type of the signal. Once we have the signal, we dispatch it with a reference to ourselves. If you're wondering about the signal class, then rest assured it is very simple. Notice that at the top, unit class is taken as a parameter to the signal class. This is how data can be transferred. The unit class itself just exposes the score and explosion prefab, which we'll use later. Building upon the first example, we've added score display, score keeper, and score logger. As you can see, the game works the same, but we can now see the score increase when we kill the enemy, and the log is added to the console. Score keeper contains just a single script, while the score display is inside a canvas and has a text mesh. The score logger is also just a single script. The score keeper registers for the unit died signal and adds up the score to a field. It also always sends a score changed signal. Notice how the signal carries two different integer variables, one for the old value and one for the new. We also override the invoke method just so that it shows up in a stack trace. The score display is very simple and just listens for the score changed signal and displays the latest value. The score logger instead just writes the values to a console. Notice how the score keeper has no idea about the existence of UI and the UI has no idea about the existence of enemies. This is desirable as it keeps the code nice and readable. Improving our example further, only one object called Exploder was added. Upon killing the enemy, we see an explosion. Looking at the implementation, we can see we just instantiate an explosion prefab when the enemy died signal is received. This way, if for example we wanted to add effects pooling, we could easily do so with 0 changes to the enemy class. In our last example of signals, a lives UI was added and a button that kills the player. We can still damage the enemy, and clicking upon the die button prompts us with a continue panel. Clicking on the respawn button instantiates the player after a 1 second delay. Clicking on the give up would bring us straight to the game over screen, which is also what happens when we run out of lives. The scene is composed out of multiple objects. First, there is a canvas for killing the player, which displays the die button and the lives. Next is the respawner, which contains the player prefab and the respawn time. Additionally, we have a game over panel and a respawn panel with 2 buttons. The respawner class does most of the work here. On enable, we register the player died signal, which is emitted when the player is killed. Notice how we're saving the player died signal to a field so that we can use it later. We're also registering with the order of -100. This means that this listener will get notified before all the other listeners. The player died method is a little bit more complicated. First, we check if we have any lives left. If so, we pause the signal. This means no other listener will get this signal until continue is called. After that, we start a coroutine that is on the continue screen. This is the coroutine that offers us the window with either give up or respawn buttons. Depending on the user's choice, our callback receives a different value: true for accepting the respawn and false for declining it. In a local method called accepted callback, we act upon this result. If the player accepted the respawn, we subtract the life, emit the life count changed signal, start a coroutine that respawns the player, and consume the signal. This means no other listener will get this signal. If he did not accept the respawn, we continue the signal, so that other signal listeners can act upon it. Respawning the player simply involves waiting a few seconds and instantiating the prefab. The continue screen has a reference to its canvas group and the 2 buttons. It also has an internal prompt state enum. We will look at it later. In dwake, we toggle our canvas to hide it. On enable, we register listeners for our 2 buttons. The registered methods both just set the internal prompt state to some value of that enum, declined or accepted. The prompt player coroutine sets the internal state to empty. We display the canvas and we wait until we get a callback from either of our buttons. After we receive a callback, we hide the canvas again. Depending on the internal state, we either return true or false. You can see the enum at the bottom. It's a simple free state enum. The game over screen is quite simple. It just has a reference to a canvas group, which it sets to 1 when it receives the player died signal. Because of our work in other classes, the game over screen has no idea about other functionality such as lives or the continue screen. The signals package also boasts very good performance. This is because nothing is allocated upon sending a signal, thus preventing garbage collection, which would slow our code down. From my experience, you can easily send 10,000 signals in a single frame, and it only takes 0.7 milliseconds. That's all from me today. Good luck on your next game.